This is a brief introduction to show how the statistical vibration synthesizer system is used to produce non-stationary and non-Gaussian vibrations. As with any random vibration controller, we need to first define the target PSD function. With the SVS system, all the target PSDs are stored in Microsoft Excel and are accessed via a direct link. This is designed to make it easier for users to define target functions. This is demonstrated here, where we have an Excel spreadsheet with a number of worksheets, with each worksheet containing information on a single target PSD. The software allows the user to browse and preview all the available PSD functions. As this is done, each target PSD is displayed at top right of the screen. Here are some PSD functions familiar to some users. The website contains a demonstration on how to generate and edit target PSD functions. For this demonstration, we will use PSD-C, which was calculated from vibration measurements on a vehicle in Melbourne, Australia. Unlike ordinary random vibration controllers, which can only produce steady-state vibrations at a fixed RMS level, the SVS system uses the RMS distribution to produce non-stationary vibrations. Here we will use the RMS distribution computed from the same vibration data that was used to compute the PSD function. Again, all data relating to the RMS distribution are stored in Microsoft Excel and are accessed directly from the SVS software. This direct link to Microsoft Excel means that all the worksheets in the Excel file can be viewed from the SVS software. Here is a list of all the available RMS distributions that have already been stored in the Excel library. The PSD needs to be updated to make sure that it matches the RMS distribution. This is easily done by reopening the current libraries. As the target PSD is updated, notice that the overall target RMS now matches the overall RMS level from the RMS distribution. The RMS distribution clearly shows that the RMS of the recorded vibrations are not constant. There is a variation in RMS level from small values up to around 6 meters per second squared. Moreover, the distribution is not uniform. This produces not only non-stationary vibrations, but as a result, non-Gaussian vibrations, as shown on the PDF graph at bottom right of the screen. This graph shows the probability density function of the target vibrations that were calculated from the RMS distribution. If we use the zoom tool, it can clearly be seen that the overall distribution is non-Gaussian, shown here as a blue line, compared with the equivalent Gaussian curve, shown in black. One useful method for determining if a signal is non-Gaussian is to use the kurtosis statistic. Here we can see that the kurtosis of a target vibration is 5, which is a confirmation that the signal is non-Gaussian. Now we have the two essential ingredients needed for producing non-stationary vibrations. The only thing left to do is to configure the test parameters. Firstly, we enter the test duration. Then we can adjust the minimum segment length, which controls how rapidly the random fluctuations in RMS level will occur. The system requires the user to ensure that the accelerometer sensitivity is set at the correct value. Finally, if the SVS RVC adapter module is used, the system needs an RVC to work. This needs to be configured with a nominal RMS level, usually set to the overall RMS level. This parameter must match the RMS level of the random vibration controller. This is important as the SVS modulates the stationary vibrations generated by the random vibration controller. Only when this value is entered that the Start button appears. When the Start button is pressed, the software computes the displacement spectrum and uses the RMS distribution to calculate the maximum displacement needed to produce this PSD function for the range of RMS levels described by this RMS distribution. The message shows that the maximum peak-to-peak displacement needed is 157 mm, which is less than the stroke of a shaker currently being used. Once the user confirms that the displacement requirements are satisfied, the software computes the modulation function as well as produces an FFT optimization algorithm to assist in performance. Before the SVS is activated, the random vibration controller needs to be started to produce stationary Gaussian vibrations. The SVS is then activated to produce non-stationary, non-Gaussian vibrations. Examples of a system in action are available on the website.